Hello, everyone. Thank you for joining us and welcome to today's online FoRCE seminar. Before introducing Dr. Lunze, I will briefly inform you about the FoRCE, the Forum on Robotics and Control Engineering. It is dedicated to providing free, high-quality outreach events and online seminars to reach broader robotics and control engineering communities worldwide. To this end, we periodically invite distinguished researchers like Dr. Lunze to give seminars on their recent research results related to robotics or control engineering. The FoRCE aims to connect academicians and government industry researchers through research discussions. We cordially hope you enjoy all the FoRCE events and find them valuable to your research. I would also like to add that FoRCE is supported by the IEEE Control Systems Society. You can find previous FoRCE talks and many other excellent talks on the IEEE CSS Video Library webpage. Now, let me mention the MS Teams logistics for today's seminar. We are all muted during the presentation, except, of course, for Dr. Lunze. If you are not muted, please mute yourself. After the talk, we will have 5 to 10 minutes for questions and answers. You can post your questions to the chat box so I can read them to Dr. Yan. Or you can just unmute yourself and directly ask your questions. Please note that this session is being recorded and it is going to be posted to YouTube as well as the IEEE CSS website. It is our great pleasure, together with Tansel, Yucelen, and Merve Doğan, to host Dr. Lunze today. He has been the head of Institute of Automation and Computer Control at Ruhr-Universitat Bochum, Germany since 2001. His research interests include network control, fault-tolerant control, and engineering applications of logic-based systems. He is the author of several monographs and textbooks, including but not limited to Network Control of Multi-Agent Systems, which was published in 2022, and Graph Theoretical Methods in System Theory and Control, which is published this year. For everyone here live, I would like to take a moment to sincerely thank Jan for participating in our forum as a speaker. Dr. Lunze, the stage is yours. Please feel free to begin whenever you are ready.
Ladies and gentlemen, thank you for the introduction. First of all, I want to thank the organizers for inviting me to give this talk. I have seen several of the predecessor talks, and I have seen that the FoRCE seminar has a very broad scope. Therefore, I have structured my presentation so that you will see several of the results that I have obtained together with my PhD students during the last about 10 years. We have dealt with network control of multi-agent systems, but not only from the theoretical viewpoint, but also for some application orientation in cooperative driving. In particular, you will see that I show you videos on platooning and also on the crossroads management. I will start with a rather broad introduction. If you hear the notion of a network system, then probably this kind of figure pops up in your mind. You see that generally we represent network systems as a graph. In this case, the vertices of our graph represent dynamical systems. And the different colors should now show that we have different properties of these systems. The arrows are interconnections that will given by digital communication networks in my field here. I will make several assumptions, and one important assumption, at least for this presentation, is that we want to deal with identical subsystems. We also will call these subsystems as agents, and these uniform colors should now tell you that we have the same dynamics in all these vertices of the graph. The idea is to look at the cooperative control task, which means that the outputs yi and yj of any pair of agents should at least asymptotically approach the same synchronous trajectory. As an idea, I show, or as an illustration, I show you that we have here the synchronization shown for a set of oscillators. The oscillators start in different angles, and after a while they join the same synchronous trajectory. We need this kind of synchronization, for example, in the distance control of vehicle platoons. That is called usually adaptive cruise controller and abbreviated as ACC. The vehicles have a radar system to measure the distance to the predecessor vehicle, and then they have their own controllers, so that we get, in principle, a very simple series connection of several subsystems. Nevertheless, you will see during my talk that in this safety critical system, we have not only to ensure that the systems synchronize with respect to their velocity, but we have also to satisfy certain additional requirements. And this will be the subject of the second part of my talk. If we look a little bit in the future, then we hope to have vehicle-to-vehicle communication in the near future, and then we can add certain new couplings. These are the red arrows here in my block diagram. Again, the overall system seems to be rather simple, as a series parallel connection of several subsystems. Nevertheless, again, here we have to satisfy specific requirements in order to have the safety of the cars. This idea can be extended, for example, if you have several lanes that and the vehicles have to join in one lane, then the synchronization problem appears in a little bit extended version. And also, if you look at these crossroads here, you see that I have a crossroads without any traffic light, without any traffic sign, and we want now the vehicles to decide themselves which vehicle should go first. And clearly the cooperative control task is to avoid collisions on these crossroads. Then clearly for a cooperation we need communication, and this might be a good communication structure for the topic. In the final part of my talk, I will show you a graph theoretical method to find out, not for the crossroads, but for a vehicle swarm, how to get the nearest neighbor couplings. So we have dealt with this problem, and we have even found a solution to this crossroads problem. And I will show you first as a motivation a video in which you see robos going on our platform. We have, these are real robos. I was asked to emphasize this point because today you see many videos with animations. This is a real experiment that we have made, and you see these robots moving on our platform. The violet arrows show the communication among the vehicles, and then these green arrows show the directions that the vehicles should go. And I will now first show you a video on that. So I start the video now, and you see first a very simple example where these three vehicles do not interfere, but nevertheless they have to be sure that they will not interfere. Now the situation is a little bit more difficult because the two vehicles on the back have to slow down. Now three vehicles go over the crossroads without any interference, but in the next experiment you see that one of the vehicles here, the right one, had to reduce the velocity, which was symbolized by these red arrows. Now we have a heavy traffic, and then in the heavy traffic clearly you see that several of these vehicles have to stop. This has nothing to do that our algorithm is not optimal, but it is clearly a problem of physics. If you have too many vehicles, then you have a reduction of the traffic. That's clear. In a moment, you will then see that we have a medium traffic, and in the medium traffic, our scheme works now quite well, because you will see that nearly no of the vehicles have to stop or to reduce the velocity. So I think it's quite fine. The idea, by the way, is that the vehicles communicate the time at which they reach the crossroads, and then in accordance to the time, first coming, first serving, they go over the crossroads. Now we see the video in a quicker way in order to give an impression that this algorithm works quite well. So you see, this is a good result with respect to cooperative control, but I have to tell you, we were not able to prove that these vehicles are collision-free. And this is the problem. Yeah, we often hear that you can have some heuristic means and heuristic ideas in control, and then you find out that by experimentation that all the system works well. But in such a safety critical situation, you need some proofs, at least for the main pillars of a new technology. You need to prove that this system really would be free of collisions in this case. And therefore, we have to start from a basic ideas and not start with the most ambitious tasks. And therefore, we come now first to some characteristics and then to the synchronization task. The idea that I have shown you now shows you three main characteristics of network systems. First, you have equal subsystems or equal agents in the sense that these subsystems have the same rights, for example, on these crossroads. You will not have a coordinator. You will not have a helicopter flying over the crossroads and saying, you should go first, you should go second. This is sometimes called the infrastructure measure. You want to have agents that themselves decide what to do, and therefore also the structure, in particular the communication structure, is the result of self-organization. You will see this particularly well in the last part of my talk, where I show you how they can have a self-organized communication structure. And clearly the task is, the task, it depends upon the current situation. If you are in front of the crossroads, you want to know which other vehicles may cross at the same time. But if you are behind the crossroads, then you have no idea, or you don't want to have information about the crossroads behind you. So it's clear that you have to adapt your system to the situation in which the agents are. And therefore, we want to do something which sometimes is called network thinking in literature. And that means we want to find a relation between the collective behavior of the network system on the one hand side and the agent properties and the coupling structure on the other side. And I will show you that for the platooning problem, we are really in the position to have a one-to-one correspondence between the collective behavior and the agent properties that I show you. And I think this is a good idea, or this demonstrates the idea of network control for our platooning problem. So I will structure my task, the remaining part of my task, in the following way. First, I will show you some results of synchronization of multi-agent systems. This may, at least in the first part, be results that you already know, but I hopefully show you then some new views on that from a contra engineering viewpoint. In the second part, I will go further with the collision avoidance of vehicle platoons, and we will see that the general theory of synchronization is not enough, is not sufficient for this safety critical problem, and we have to deal with additional requirements. And finally, in the last part, we want to have or let our ideas a little bit go further and say, why should the vehicles go along straight lines or straight lanes? Let them go in an arbitrary way in the plane, and then we have vehicle swarms, and I will show you how we can avoid collisions even under this condition. So let's start with the synchronization problem. And first, I want to introduce my notation for graphs. I show it by the example graph on the left-hand side, but these results can be extended to the weighted graph on the right-hand side if you replace the ones that I have here in my matrices by the weightings or by the labels of the edges. So first, the adjacency matrix in my notation is the following. AG is the adjacency matrix, and in the fourth column and the first row, this one signifies that we have an edge from the vertex number 4 to the vertex number 1. Some notation is different in the sense that they take the transpose of this matrix. I take this kind of adjacency matrix. Then I get the in degree of the agents by summing over the rows. And for example, these two here means that I have these two elements in the adjacency matrix on this side. And it means that the vertex number 2 has 2 incoming edges. What we need for our model is the Laplacian matrix, which is the difference between the degree matrix and the adjacency matrix. And probably all of you know that in the Laplacian matrix, in the main diagonal, you have the in degree of all the vertices, and outside of the main diagonal, you have non-positive elements. All the minus ones here are showing the edges that we have in the graph. An important property that we need later is that the Laplacian matrix is singular because the row sums to 0, and therefore it has one eigenvalue, which I denote by lambda 1, which is equal to 0. And the second eigenvalue, so to say the next eigenvalue then, is non-zero if and only if the graph possesses a spanning tree. These are results from algebraic graph theory. Then we can come now to the model of the multi-agent system. I denote the agents by P1 through Pn, and I describe them by a state space model. I have scalar input ui and scalar output yi in order to simplify the notation. Then I have xi dot equal to the matrix A times x plus b times u, and here we have C transposed as the vector to be multiplied by xi to get the output of the agent. The matrix A usually is not Hurwitz because in synchronization we want to have these systems moving along a non-trivial trajectory, and therefore we have eigenvalues with non-negative real part. The controller is a controller that feeds back the difference of the output of the ICE system and the output of the neighboring systems. And this is a specific controller that is also called a diffusive coupling in literature. And these Aij that I have in front of it are the elements of the corresponding adjacency matrix. So it is clear that I sum over all the neighbors, at least over all the indices, and not all the indices have non-zero elements Aij, so that not all the agents are neighbors of the ith one. Okay, in a more general way, I can represent these controllers in a vector matrix form, in which I use Laplacian matrix that results from this graph. But here, the L hat should be a normalized Laplacian matrix that is used when I introduce an additional controller gain k, so that I have now the network controller in this form. Both together, namely the model of the agents together with the model of the network controller, gives us the overall system that I denote by sigma bar. And I have now here in the state vector x all the states of the agents 1 through n. And I have here a huge matrix in which you see the Laplacian matrix L. I find this is a very interesting result in which you see that the representation of a graph appears naturally in the model of a dynamical system. So I have these connections between graph theory and dynamical systems, and we can exploit graph theoretical properties when analyzing the overall system. This system does not have any input because it starts from an initial state and then it moves along the trajectory that is described by this model. So now let's define what we understand of synchronization. We say that the overall system is said to be synchronized if for all initial states of the agents we have the relation that I have already shown you, namely that the differences between all pairs of outputs of the agents asymptotically vanish. This is the definition, and clearly we want to have a necessary and sufficient condition for synchronization, and this is a rather old result. You see here that Pecora and Carroll, two physicists, have proved the result in 1998. Rather early from our current viewpoint, and the result says that the system is synchronized if and only if several matrices that I have written here are Hurwitz. And these matrices, these test matrices, in these test matrices, we have the elements A, B, and C transposed of our agents. These were from the model of the agents. And then we have the eigenvalues of the Laplacian matrix, with the exception of the first eigenvalue. You see the enumeration starts with 2 through n. The vanishing eigenvalue is not applied here. This is really an old result. I have read the original paper. I'm not quite sure, but I expect that as physicists, Pecora and Carroll have proved this result for nonlinear systems, because I cannot imagine a physicist that uses linear models. But at least for our situation, it is clear that we have these linear equations and we can exploit them now in the further way. One result which is well known in literature is that from this theorem we can derive as a corollary a necessary synchronization condition, which says that the lambda 2 of L has to be non-zero, because we have to stabilize, so to say, the matrix A by this feedback that we have. And this result transferred to our graph means that the communication graph must possess a spanning tree, which I have here shown as for an example graph. And this is clearly an intuitively clear result. If I want to have the overall system synchronized, then I need at least one agent that has a contact or is in contact with all the other agents. But the interesting point is that we can derive it in a very systematic way from our model, and not introduce it as an intuitive explanation or intuitive result from the analysis. Another result, which might not be that well known, is that from this theorem we can derive the property of synchronizability. Control theorists are keen on having properties that the plan should satisfy in order to be able to control the plant. We know controllability, observability, stabilizability, and so on. And now we have the property of synchronizability defined in the following way. Agents are said to be synchronizable if for any number of them there exists a network controller such that the overall system is synchronized. That means we have a property that if it is satisfied, then we get a network controller that does the job. And if it is not synchronizable, then we have no chance to do it. And this is quite an interesting result, because engineers hopefully have such existence conditions. Otherwise, they would probably try until the end of their life to get a solution without having a chance to get it. So how do we get a result on that? And let us look again on our test matrices. The test matrices are AI bar, and they look like the matrix of a feedback control system. Namely, I have the agent A, B, C transposed, and I feed back the output to the input, and with the gain minus lambda I of L. So I have an output feedback system, and I require that an unstable matrix A should be stabilized. So to say, I mean, and matrix A, which is not Hurwitz, which has eigenvalues with non-negative real parts, should become a matrix which has only eigenvalues with negative real parts. And this is the problem of stabilization of the agents by an output feedback. And therefore we get the theory, agents ABC are synchronizable if and only if they are output feedback stabilizable. Unfortunately, for output feedback stabilizability, there are also only partly necessary and sufficient conditions. But I will show you for an example that we can use this result directly. Namely, in literature, very often we have oscillators used for synchronization illustration. And you have an oscillator like that here with the frequency omega. And if you have this input and this output, then you get for the matrix that I show you here, in dependence upon the controller gain k, this root locus. And you see at once that you have no chance to stabilize this oscillator by an output feedback. So I don't understand the long discussions in literature that use this kind of oscillators and then discuss the problem how to synchronize the system. This kind of system simply is not synchronizable. The situation changes if we have another input, so to say another actuator in the system. We have this additional one here in the B vector. Then we get a system that has also a zero here, and therefore this zero changes the root locus, and now we have an interval for our controller gain in which the feedback system, the oscillator together with the output feedback is stabilized, and that means these output, the oscillators are synchronizable. Then we can really use this root locus here in order to find a particular controller gain k. We use this controller gain k for a Laplacian matrix, and then we get the result that I have already shown you for illustration of synchronization, namely these oscillators synchronize on a sinusoidal trajectory. So this is the idea to show how we can interpret our theorem on synchronization in the sense of synchronizability. Another probably new interpretation of the system is a control theoretic interpretation that we have used in order to introduce our network thinking to these oscillator networks, or also for our Wiegel platoons. Namely, until now we had the situation that the Laplacian matrix was the controller matrix for the network controller. But clearly we want to have, in a better way, the adjacency matrix of the graph as the coupling matrix. And we get that by introducing a feedback controller for all the agents. That means we have local controllers together with this communication network. And to get this situation, we have simply to use our couplings and reformulate it in the following way. We use the summation over the weighted outputs of the neighbors in order to introduce a local reference signal, which I denoted by YSI. And this is the weighted sum of all the neighboring outputs. Again, this hat over the Aij means that I have normalized adjacency matrix used. And then I can reformulate the original version of my network controller in this way. And you see here, this is the usual way of a usual control law, namely minus controller gain multiplied by the control error, Yi minus the command signal. And this means that we have now reformulated the overall system in this way. We have local controllers in the agents, and we have the communication network. Here you see in the last line that we have the inputs to all the control agents given by the adjacency matrix of the graph multiplied by the outputs. And then we have here already a feedback controller in the system that you see also here in this matrix. This situation occurs in our platooning problem. In the platoon, the vehicles have a radar system in order to measure the distance to the predecessor car and also the velocities of both cars. And then we can reformulate our platooning problem in the following way. This is now the model of an agent together with the controller. It seems to be a little bit complicated, but let me show you. We have here a velocity control loop. This is included in the vehicle. this UI in our notation, the input to the agent is now the set point or the command signal for the velocity. The control loop produces the right velocity, Vi, and by integration I get the position. Then I subtract the required distance among the vehicles in order to get really a synchronization problem where the outputs of all the vehicles should become the same. Also, clearly, the vehicles should have a distance among each other. And this is due to this subtraction here. And then the output Yi is fed back over the controller Ci, which is our network controller, or part of our network controller. And the input to the system YSI is then for ACC simply the output of the predecessor car. And for the cooperative adaptive cruise controller, it is the mixture of the outputs of predecessor cars. I have, as an example, now said that I know the output of the predecessor and the car in front of it, and I take the average of the two as the output. This is simply for, as an example. Clearly, for CACCC, you are able to have any communication structure. So if I now use our synchronization condition, I clearly have to reformulate the whole process in the way I have stated the synchronization problem. So I have no longer the adjacency matrix, but again, the Laplacian matrix L. Nevertheless, you see that the Laplacian matrix now is a lower triangular matrix. So we have the eigenvalues in the diagonal. All eigenvalues are 1, equal to 1, and the test matrix is A minus BC transposed, which for the elements that I have used, for the example that I have used, is Hurwitz. So we have the synchronization requirement satisfied. And the same holds true for CACC, namely now we have these minus 0.5 in the two rows below the diagonal. Again, we have these eigenvalues all equal to 1. We have the same test matrix as before. So also for the CACC, we have synchronization. And if we make a simulation, then we see that the red curve, which is the velocity, or the position, pardon me, is the position over time. The red curve is the position of the first vehicle, and all the other vehicles start far behind the first vehicle with different velocities that you see in the slope here. And then finally, they have the same velocity and have, so to say, a good synchronized behavior. So I want to summarize what we did until now. First aspect was that I have shown you that the model of the overall system includes Laplacian matrix L or the adjacency matrix AG as the element which shows the connection between dynamical models and the graph, a theoretical structure of the system. Second, we have seen that the synchronizing controller has to satisfy a necessary and sufficient condition for synchronization. And the third problem was that we have seen that the agents have to be synchronizable in order that the overall problem has a solution. The question now is clearly, does this solve our problem? Our problem, I mean now, the safety critical problem for our platoon. Can we now use this controller and go on the highway? And in order to convince you that this is not the case, I go one slide back and show you again this figure here. What we could prove is that here for a long time, namely here at the end of the trajectory, so to say, we have synchronized behavior. But what we did not consider in our synchronization problem is what happened here. And here, this looks quite nice. So this situation will not bring some collisions. But if here we have curves that cross each other, then it's clear that our vehicles will collide. And therefore, we have to go further into our problem of collision avoidance of vehicle platoons. And that is an effect that I wanted to show you, namely that if we want now go to some practical application, we usually have to extend a general theory that is applicable in many fields in order to solve the specific problem of the application field. And the application field now is this ACC system, namely a vehicle row together with a distance controller. If we want first to write down all the requirements, then we have in overall 4 requirements. You see that I have deleted, or I have not written down the first requirement, because this is a standard requirement that the control loop should be asymptotically stable, that we clearly require here. But therefore, my enumeration starts with number 2, synchronization. That's what we have just shown. And we have now 2 different additional requirements. The first one is the so-called time headway policy. We want to have a reference distance, the distance among these vehicles, if the velocity is constant, which is equal to beta times the velocity plus alpha I. The alpha I is a distance that is obtained when the vehicle stands still. I will avoid this additional addend by saying, okay, let's think alpha I is equal to 0 to simplify the notation. But then we know that we have this beta I times Vi as the reference distance. Beta I is also said to be the time headway coefficient. The time headway coefficient you have learned in the driver's school is 2 seconds. I have to emphasize this situation, because if you go on a German highway, then you feel that people think 0.2 seconds is the time headway coefficient. Yeah, we see many accidents on our highways simply because people do not know what is the usual distance that assures a collision-free movement. Therefore, we want to think of, say, 1.5 seconds or 2 seconds as the beta coefficient when we discuss this point later on. And the 4th requirement is collision avoidance, which means that for all arbitrary profiles of the velocity of the leading vehicle, we want to have a distance which is positive. Clearly, it may be larger than alpha I, but we can simply say that di should be positive, or non-negative at least, and then we have this collision avoidance. And now we have to go through these requirements. Before I do that, I want to have a short retour to string stability, because in the literature, and also in the scientific literature, but also in industry, people think that the property of string stability solves the problem. As you see here by my first reference, 1974, it's now 50 years of string stability that we can celebrate. Although I will show you that string stability does not the job. Because I will show you now that a string stable system may have collisions. And this is a very important aspect. And personally, I have to say, I do not understand why people stick to this property, although it's now clear what they really have to do. And I want to show, shortly characterize what string stability is. We look at this row of vehicles, and we consider one vehicle alone. And the vehicle input is either the velocity, then also the output is the velocity, or it is the position or the distance to the predecessor vehicle, and then it's also the distance to the next vehicle as the output. That doesn't matter. And now we require that the transfer function from here to here, or at least the frequency response, needs to have a magnitude less than 1. Which means that if you think that you have a sinusoidal profile, that means a sinusoidal velocity profile, for example, then the velocity of our own car is also sinusoidal, but has a magnitude that is not larger than the first one. And so the idea is now, if you look again at the vehicle row, then you have a sinusoidal input to the first vehicle, and the sinusoidal coupling signals have a magnitude that is lower than the magnitude of the vehicle before, or in front of that. And this is true, of course. However, if you now think of the step response, that means you jump to a system, then you have overshoots. And the overshoots even in a string-stable system, may increase. And that means if you have a certain jump in your input signal, then you find a length of the vehicle platoon where the last vehicles collide. And therefore, string stability is not sufficient for satisfying our requirements of collision avoidance. Here you see a typical velocity profile, at least at the German highways where we have many construction sites. So you are allowed now to go further, you are quicker, and then you have to slow down and so on. This is a very typical situation. Here we have 50 cars in a row, and then you see here the distance among that is negative. And negative distance means you have collisions. So that means we have now to start again with our vehicle row and look again at from a new viewpoint at these vehicles. I will use this structure of my model. You see that I use the velocities as the coupling signals. And we have two transfer functions. I go now in the frequency domain. Gi bar is the transfer function from the velocity to the velocity as the output, and Fi bar is the transfer function from the input velocity, that means the velocity of the predecessor car, to the distance to the predecessor car. So if I now write down the equations for one vehicle, then I have the velocity here as the output and the distance here as the output. This tilde I have explained here is the reduced vehicle distance because I now subtract these alpha I that I have introduced before. An important aspect is that these two transfer functions are not independent, but this Fi bar is equal to this formula here where you see the Gi bar in it. So that means in principle it is an integration that we have to introduce for the difference of the two velocities in order to get the distance here. So, and that means we have, so to say, only one degree of freedom in choosing these transfer function. And the problem now is to find characteristics for Gi bar and Fi bar such that the controlled vehicle, if it is on the highway with other controlled vehicle with the same properties, avoid any collisions for any profile of the first car. So I have used the model here with VSI, my local reference signal, as the input. But first we look at ACC, the adaptive cruise control, and then this VSI is simply the velocity of the predecessor car. So now let's first start with R4 with the collision avoidance and then go back to the other requirements. What we require now is that for an arbitrary function Vi minus 1, namely here input, which is non-negative, we want to have an output of this system which is also non-negative. So we have a dynamical system. Independently how this controller and how this vehicle is realized in practice, we have a dynamical system, a linear dynamical system in this sense, and then for any non-negative input it should have a non-negative output, and this is called an externally positive system. This is a standard property of linear systems, and we also know how to check it, namely the impulse response of the two transfer functions that we have here and which are denoted in my notation as Fi bar of t and Gi bar of t have to be non-negative. So if we have a car, we can check whether this car is externally positive. And if it is, then we know that collision will be avoided in any vehicle platoon with such cars. You can, by the way, check whether this requirement is satisfied for your own car if you go to the highway. You choose a lane in which you have free space and one car is in front of you, and say you are going with your own car 20 kilometers per hour quicker. That means that the first, in a long distance, your radar system will not say anything, and you will go with your required velocity. And then you will come to the situation where your radar system recognizes the vehicle in front. This is about 100-meter distance. And then usually you also see it on the dashboard. So, and then you say, now it's interesting, what happens? And the usual way, if the system is externally positive, then it reduces the distance to the predecessor car monotonously, without any overshoot. This is an externally positive system, and you should check it when you go next time on the highway, and you have not a traffic jam, of course, but you have a free place. Because, for example, in my car, which is now 4 years old, this requirement of an externally positive behavior is not satisfied. So in principle, I should have to switch off my ACC. But as a control engineer, I like this system, and therefore I go with it. Nevertheless, I know that I'm in danger, because if many of these cars would go, then we can imagine a situation in which we have collisions. So it is not only sufficient to solve the problem, but we have also to apply it. Okay, second requirement was synchronization. For a constant velocity, we want to have the same velocity as the output here. This is a constant velocity. We have the same velocity finally in my car, and that means that simply the static reinforcement of this system here, of this part of the system, has to be 1. How we will get it, we have already solved, but now we look not at the vehicle alone, but we look at the vehicle together with the controller, and then it's important to say what does it mean for this vehicle. And the final requirement was time headway policy. Now again, we have this constant velocity at the input, and we want now to have beta I times this velocity as the output here. And that means that now this static reinforcement should be equal to beta I. This is only a formal problem. The question is clearly, what does it mean? What does it mean? So I take it here. I determine now this Fi of 0, the static reinforcement for this transfer function. I use the formula that I have already shown you, and then I use some formula that you learn in the control course with Laplace transform. And then you know, or you see that we have to integrate over 1, which is the final value of the step response, minus the step response of this system here. And this integral we denote by delta I. And now we see that time headway policy requires that this delta I is equal to the beta I that we have. Again, we have to ask a question, what is this? And therefore, we look at these drawings here. We consider the step response. Step response means that the input to the system is a step input. And then we have the step response. The step response does not have any overshoot because we have an externally positive system. And then this integral that we see here is the area between our step response and the final value. This is delta I, and we can determine the delta I for any given controller, any given vehicle. But clearly, to have a step here at the velocity of the predecessor car is not a practical situation. A practical situation is more this. We have a certain velocity denoted by V0 bar. And then the vehicle in front of us increases the velocity in a certain way. Our vehicle, which has the velocity Vi, increases the velocity to the same value, but clearly a little bit later. Again, we have an area between these two curves, and we can prove that this area is again delta I times now this step here, namely Yi bar minus Y0 bar. And you see that this delta is a characteristic property of our controlled vehicle that says how which is the value of the distance that I add if the velocity is increased, and if in a maneuver that the velocity is decreased, which is the distance that between my car and the predecessor car will be decreased. So in summary, we see that we were able to have the properties of the platoon represented as properties of the vehicles. Synchronization is obtained if we have the static reinforcement of 1 for the GI bar. Time headway policy is satisfied if we have delta I equal to beta I, and the collision avoidance is satisfied if we have an externally positive system. So here I have really the situation that network thinking works in the best possible way, namely that the properties of the overall system for the collective behavior of the cars in a vehicle platoon can be broken down to properties of the vehicles. If all the vehicles have this property, then we have a situation that you see here. Namely, again, you see the velocity in the left upper drawing. Then you see here the distance. You see we have a distance that is larger than 0 for all the time. If you compare it to the string stable system, of course. And here you see the position, and so you see as a control engineer, that's a quite nice view. You see that the dynamics are quite well. So what we have now is that the requirement that all the vehicles have to go in a distance to the predecessor which corresponds to their delay. If you have a row of small vehicles, then all the vehicles have these 2 seconds as their delta I, as their delay measure, and then you have all the same distance among the vehicles. If then you have trucks, these trucks do generally have a change in the velocity which is slower. They are not slower in their final velocity, but they are slower in the change of the velocity because the acceleration or the braking acceleration is slower. Then they have to have larger distances. So if you use this requirement that delta I is equal to beta I, or other way around, if you go with beta I that corresponds to your delta I in your vehicle, then we are done with ACC. We do not need any communication. However, if we want to have the small distances also here between the personnel cars and the trucks, then we clearly need some communication structure, the communication network, and with the communication network and an appropriate communication structure, we find that we can go with a shorter distance. It's interesting to know that we have found a design method for the communication structure of CACC. That means we should not have a heuristic trial and error method, but we can really determine by some formulas, namely the formula I showed you here, some inequalities, from which vehicles in front of it, a certain car should get information. And I cannot show now the whole algorithm because I do not have the time for that. And it's also a little bit complicated to go through all these inequalities. But the idea is the following. The car should go with the distance beta I times Vi. Beta I is smaller than delta I. Therefore, the usual way would be without communication to have this distance as is the distance for the track. And therefore, we have a virtual car now here that we can approximate by information coming from this vehicle and from that vehicle. And in the mixture, we get the information about this virtual car. And then this car reacts in terms of this virtual car. So we need communication in order to realize this virtual car. This is the idea for this communication structure design. The term design is used because we really have a systematic way how to come to the communication structure of that. As I said, this is too much now for the presentation I give here, but I will show you in the last part of my talk for another situation how to get the communication structure. In summary, we have seen that the requirements on the platoon can be broken down to requirements on the controlled vehicles with these 3 parameters that I have shown you. And communication is necessary only for vehicles that want to go with a smaller distance that in comparison to their delay delta I. If beta I should be smaller than delta I, then we need communication in order to introduce this virtual car that I just mentioned. With this, I want to go to some outlook. control of a vehicle swarm. And I want first to say we came to the vehicle swarm on the right-hand side to consider this swarm, and in particular the design of the communication structure that is shown here in yellow, because we considered several situations that extended the vehicle platoon in a certain way. This combination of lanes here or these crossroads here, and we thought we don't want to consider all these different situations for the vehicle separately. We simply want to take a vehicle swarm and try to avoid collisions by a controller. And the idea that I cannot now go into much detail now consists of three elements. First, we need local controllers that make the vehicles externally positive. You know already why it is the case, but now it is the case not only with respect to a longitudinal behavior, but clearly with respect to an arbitrary behavior in the XY plane. The second is that we use the potential field methods that is well known in robotics in order to find out what is the command signals for the vehicle controllers. And in particular, my PhD student Alexander Schwab used Morse potential fields in order to get command signals for which we do not extend the limits of the control inputs. So we can respect control limits for our input limits. And the third idea was to use the Delaunay triangulation to get nearest neighborhood communication. And the last part I will briefly describe in the last minutes now of my talk. A triangulation, I have to say first, is you have given a set of points that I have here represented by nodes of a graph. And you want to decompose the convex hull of this set of points into triangles. And you see here two triangulations for the same set of points, which shows you that triangulation does not have a unique solution, but several solutions. We want now to investigate these two triangulations with respect to the nearest neighborhood. For example, if we look at this agent here, then this agent is the geometric neighbor of this, but we see that we do not have a direct communication in this triangulation, whereas here we have. And the same situation here, one of the direct neighbors of this agent here is that agent, but we do not have a direct communication, but we have it here. So we need a specific triangulation, which has been elaborated by Boris Nikolaevich Delaunay about 100 years ago. And Delaunay required the following. For any triangular that you see here, like this blue triangular, we draw the circumcircle. And then we require that no other point lies in this circumcircle. And then if this is true, then we say that this triangle is Delaunay. Delaunay is then used as an attribute, okay? You see the blue triangle is Delaunay, whereas the gray is not Delaunay, because this is again a triangle. We have here the circumcircle, and we have here at least two vertices lying inside of that. Therefore, for us, it was the problem how to find out under what condition is a system Delaunay, and how can the agents themselves determine a Delaunay triangulation. And I can describe this idea by means of these four elements, A, B, C, and D. You see that in the left situation, A, B, and C have this circumcircle, and D is outside, so A, B, C is Delaunay. Then the agent moves into this direction, and then it comes to the situation that it is on the circle. It doesn't matter. Again, ABC is Delaunay, but if the agent D is moving further, then it's clear that the Delaunay requirement is violated. And now we have to make what is called a Larsen flip, according to Larsen, who has published it. Namely, we replace the direct communication between A and C by the communication between B and D. And then we retain the situation that now we have two triangles that are Delaunay. This is a situation that can be understood, and Larsen also had proved that after a finite number of Larsen flips, at least of this extension of the communication links, we get a Delaunay triangulation. For us, it was important that we can do it from the viewpoint of the agents. Namely, we use these two matrices that I have written down here. You see that these matrices consist or include the x and y coordinates of the point A, B, and C, and here also of the point D. If you now take the viewpoint of agent A, then you see A knows its own position, and it gets the position of D, C, and B over the active communication links. So A can determine both matrices, and then it can determine the determinant product of both matrices, and if this is less than 0, D is outside. If it is equal to 0, D is on the circle, and if it is positive, then A knows that the edges have to be flipped. The same holds with C. So you see that we have really the situation that we can decide from the viewpoint of the agent how to get the Delaunay triangulation. We have applied that to our experimental setup, and I will show you now the video of that. Let me see. So you see that first, due to this Morse potential field, the robos come to a certain position, and now we have one of these robos controlled by a joystick. What you see with the white edges is the Delaunay triangulation, and you see I think it's a good illustration how these Larsen flips make the triangulation to remain a Delaunay triangulation, even if this vehicle moves. And you see also that usually only the vehicles that are nearest to the vehicle that we control from outside find or have to react on what we have seen here. So with this, I come to the conclusion. I have shown you that cooperative control needs communication, and there are systematic ways for the design of the communication structure. This is, by the way, one important aspect that I like very much in the whole field of network control, not to have heuristic means, but to have a systematic way to get it. The second is the idea of network thinking. For our collision avoidance problem, we were able to break down the overall system requirements to properties of the subsystems. If all vehicles have these properties, then we know that we have no collisions. And finally, on a more general way, I have shown you that we should give the controlled subsystem the autonomy to decide about their links also to the neighbors in order to get a communication network as a result of self-organization. I will end up with two literature. The first is the PhD thesis of Alexander Schwab. Alexander was the one who had the idea with the triangulation and the Delaunay triangulation in particular, and he is also the author of the experiments that I have shown you in the videos. And finally, I want to show you the two textbooks that I have written about network control. The left part, the left book also includes synchronization, not only for the linear case, but also for the Kuramoto oscillators that are well known in literature. And it also includes the idea of the communication structure design. And the right book combines graph theoretical methods with dynamical systems theory. And it includes, for example, these ideas with the Delaunay triangulation. With this, I thank you very much for your attention.
Thank you, Jan, for this excellent talk. I really like the tutorial style you gave for the synchronization of multi-agent systems and giving the old definition synchronizability and so on and so forth. And then switching to collision avoidance in vehicle plotons and providing the all characteristics in terms of the individual system dynamics, infrastructure, and the solvability of the problem. That was an excellent talk to me. So it is, I think, time to take questions from the audience. If you have any questions to Dr. Lunze, you can directly ask them by unmuting yourselves, or you can just put them in the chat, and then I can read them to Dr. Lunze.
This is normal. Our audience is shy. Burak, if you have questions, you can start.
Actually, I have one question about this, the characterization of collision avoidance in vehicle platoons. So we had three, I forgot what they were, but synchronizability,
synchronization at the time headway distance and the collision avoidance.
Exactly. And then we have the corresponding requirements related to vehicle parameters. So, yeah. And we were saying that G sub I of 0 needs to be 1. So basically, since this is a sufficient and necessary condition, this means that it is impossible to solve the problem if Gi of 0 is not equal to 1. Am I right?
Yeah, but Gi bar.
Gi bar. Okay.
This bar in my notation means that you have a closed loop system. Okay,
and okay, you have so the we have control over it. It is not.
Yeah, you have the vehicle together with the local controllers, and these Gi bar of 0 equal to 1 simply means that you have a set point following. Yeah, you see, you have a set point for the velocity, and then you reach the same velocity at least asymptotically. This is so to say a matter of course if you have a velocity control loop, but I need this one for the next step, namely to show you what this delta I as a delay measure is, namely to find this area between the step response and the final value. And therefore I have to first, before that, I have to show you that the final value will be 1.
Yes. Okay. So, it totally makes sense. Yeah.
How to get it? I have shown you in the second part. Yeah, synchronization, and it is also possible to have this synchronization by means of a proportional controller, because you have these integrators in the model of the system. Yeah.
Right.
So all, it is already all the basic ideas of control engineering are satisfied.
Yes. Yes. I'm looking at the chat whether we have any questions there, but no.
I have a question.
Go ahead, Mete.
Okay. First of all, thanks for the presentation, by the way. I find it very useful and valuable in terms of seeing how the theory we saw applies in practical situations, especially the platooning problem. The first example you show us, I saw that the graph is not constant, so it's switching as the traffic about the junction point intensifies or degrades. And we have this spanning tree assumption as well. So I feel like there are some time instincts that the spanning tree assumption might be violated. So how do we overcome this situation?
I understood that you now are concerned with the synchronization problem, right?
Yes, that's correct.
And I have shown you that if you want to synchronize a system, then you have to have a spanning tree, which means that you have to have at least one information flow from a specific agent, which is the root vertex of the spanning tree, to all the other agents. In this situation, if you only have the spanning tree, then you can solve the synchronization problem, but then you have a leader-follower structure, which means that the root vertex of the spanning tree prescribes the synchronous trajectory. This is in the leader-follower structure, in any case, the same situation, namely the leader describes what the others should do. In a more general way, in synchronization literature, this is not what we really want to have, because we want the agents to agree about a certain trajectory, which they then all follow. And therefore, we see that the spanning tree is only a necessary condition. We get synchronization in this situation, but what we usually want to have is a mutual synchronization. That means all the agents take part in the determination of the synchronous trajectory, and this is the case if you have a connected graph. That means you need more than the spanning tree. And the spanning tree is, so to say, the usual necessary and the least condition that you have to satisfy in order to get synchronization. This is well known in literature, but I think that the other situation is much better or much natural.
Okay, thank you for your answer.
So there is another question in the chat. I would like to have your view about future research directions in the field of multi-agent robotic systems. So
I'm not working in robotic systems, so I cannot answer the question with respect to robotics. But clearly, with respect to networked systems or networks in a more general way, I think that, as I have already said, the problem of finding an appropriate communication structure is a very important one. If you look in literature, then you, for example, have papers on optimal design of the communication structure. But this means that you need a certain entity that has the full information about the agents and the full information about the communication. And then you can use some optimization methods in order to find the best possible communication structure. But this is, from my viewpoint, not the idea of network system. In network system, you want to have agents that are on the same level of autonomy, and the agents themselves should find out what is a good, probably not the best communication structure. And therefore, I showed you in the final end of my talk that we managed to do it, at least for our vehicle swarm. Clearly, here in this situation, we only wanted to have a communication structure where the nearest neighbor agents are connected to each other, and clearly also some further agents. But the most important problem was, what is now in a swarm a nearest neighbor of mine? And this is what we have solved by this Delaunay triangulation. But clearly, you may consider other situations in which the problem becomes more involved. But I would stick to the situation that the agents should do themselves at most of the task and not introduce some kind of coordinator or supervisor or whatever.
all right, if there is any other questions, I can directly ask them to Dr. Lunze. If not, you can also, you can also email to him if it is okay with you.
Yeah, of course. Yeah.
All right.
The email was on the first slide, but if you go here on my website of the books, you will also find the email address. No problem.
Yeah. All right, then I would like to thank you again for sharing your Friday evening with us. So I know because of the time difference, it was Friday for you and evening for you.
And I hope that you will have a good Thanksgiving Day.
Thanks a lot.
Yeah, I learned before my talk, yes. Okay,
all right.
Have a nice evening. Or nice day.
Have a nice evening and have a nice day for the people in the United States and maybe in this field of the world. We hope to see you all again in another FoRCE seminar. Take care of yourselves. Bye.
Thank you, everyone.
Thank you, everyone. Thank you, Jan. Bye-bye.
Thank you.